to the project. So last time we had this presentation. I believe I'm gonna share it with you, like I'm gonna convert it to a PDF or something and share it with all of you. And in the earthquake analysis, well, you have to understand every details about the standards, how they do earthquake, but maybe I don't want to overwhelm you with lots of information at this point, so I make lots of simplification, either when I was illustrating how we do the dynamic analysis. The codes, like in the codes, you have to go through the ESE 7 standard, read how they do design for earthquake engineering, understand the science or the research behind every parameters they use, like the site factor, the risk factor. Read all this so that you can understand how the standards are handling the different building occupancies and how this impacts the risk factors. So I would recommend, if you have time, try to read this, because this, if you are going for your BE exam or something, this is very, very important. Okay. All right. So let's assume that we all are right now good in earthquake, understand the concept of responsive spectrum, or understand of the concept of seismic analysis. All what we need from the seismic analysis, we have a building like this, is gonna hit with a seismic load. Can you guys see, or I need to turn off one of the lights? Okay. So the main objective from the seismic analysis is to get the total force on the building. So it's like design for dead load or live load. The main thing for designing for dead or live load, we need to know how much load the beam or the slab is gonna have, and then design, like do analysis and get the internal forces, normal, shear, and bending moment. Same thing with earthquake. We need to have the loading. The loading is not direct, like it's not like dead load or live load we have on the flooring 200 kilograms per meter square or something. It's not direct like this. It's like a function of time, something that keeps changing over time. So we need to see how this time changing function or time changing load is gonna impact our building. Well, we can design at different time steps. Like you can say, oh, this building is gonna have this moment at this time step and can have this moment at this time step. We pick the maximum, if you guys remember, and design for the maximum. And that's what the responsive spectrum do. It tells you what is the maximum acceleration that this building is gonna have if it got hit with this earthquake, okay? Once you know the maximum acceleration, you can multiply by the mass of the building with some manipulation in the formula and find out how much force that this building is gonna have. So responsive spectrum basically converted this whole seismic earthquake sign to one single force at the face of the building. That's what we have been talking about for 2 lectures. How we can convert a seismic load from a dynamic load to one base shear at the building. Once you know that this base shear at the building, you can identify how this is gonna impact your building. Can you imagine, like, you have your building and you shake it very hard with a force from the base, what is gonna happen to the building? Okay, then ETAPS is gonna run dynamic analysis based on the base shear that it has at the base, and then find out all the internal forces in the columns, the drifts that's gonna happen and everything. So that's the summary of seismic analysis or lateral load analysis for buildings. It's all about load quantification, and that's what we do through responsive spectrum analysis. Once we quantify the load, we apply it to the building and run a model or a dynamic model for the structure. Okay. All right. So I just want to show you what we are going to do for the project. Okay. All right. So let's. Okay. You're going to go here to Google and search ASCE 7 hazard tool. Okay. And then once you search this, you are going to tell this tool everything that you know about the hazard, like what is the risk category if you're building, what is the soil type of the building. You are going to tell all this information, and then this hazard tool is going to save you the time that you need to go to the standards and identify what is the site factor, what is the like all the information that I was presenting, rather than going in the code. So you are gonna check some boxes, identify the location of your building, and I'm gonna show you right now, okay? Okay, let's see. So basically, there's different ways that we can do that. We can put the address of the building, we can put the latitude and longitude, or we can locate it on the map. So what we are gonna do, we are gonna like assume that the building is, for example, on Los Angeles, or let's search. Actually, yeah, maybe San Jose or something. Let's pick this location. So I'm gonna hit find on a map, and then I'm gonna hit San Jose and put my building is here. And then we're gonna go one by one. It's gonna ask you what standards that you want to design for. I want to use the recent ASCE 722. Not much difference from ASCE 716. Select the risk categories. Do you guys remember the risk categories? Okay, depends on the building occupancy. And then the site class, the site soil class, we are gonna pick C, so it's very dense soil or soft rock. So that's the soil we're gonna use. And then is ask you what load that you want to design this building for. I want to design this for seismic. And then I want to view the results. So it's gonna take a second. It shouldn't take that much time. Says not available with criteria selected. Okay, let's refresh this. Do it again. Find on the map. And then let's pick somewhere here. Risk 2. So class C, seismic. Okay. And here we got summary, and here it gives you all the information that we need. It's gonna give you what is the seismic. Okay, so here there's 3 acceleration. If you guys remember these acceleration, I told you that there's a map in the standards. You bet on the map, you are gonna get full values. And then you are gonna multiply by site class, is gonna give you this value. Do you remember? Depends on the soil. And then there's something called the design acceleration, the design spectral acceleration. You multiply the one that you got by 2/3, then you are gonna get these. And these are the ones that we are gonna use. So we get this. So it did everything. And then tell you what is the long period, like what is the maximum period. It's like 12 seconds in this zone. And I believe that's everything you need. Okay, so let's see. So that's the tool we're gonna use, and then we pick the parameters and go to ETABS and apply this load on the building. But we need to define this load first before applying it, okay? All right, so let's see how we do this, okay? If you guys remember from the geometry. All right. That's unlocked. All right. So I want to do a little bit of modifications on this building first before I start putting the lateral loads. So, okay. What I'm going to do, I'm going to make this slabs, all the slabs here as a diaphragm. So maybe I'm going to choose this slab, not only one. I'm going to make this all the stories. And then I'm going to choose this slab is going to choose all the slab in the whole model. So I have 60 shells picked. And I'm going to assign shell, and you will find something here. It's called diaphragms. If you guys remember, diaphragm is going to make this slab. I'm going to assign that from 1. So this one is going to connect all the point on the same slab to all have same degree of freedom. You see, like it makes line to every single joint on your slab and connect them with the center of mass of the slab. And this diaphragm, it's like implicitly, it ETABS do like, rather than all the points are gonna move or gonna have separate degrees of freedom, we all are gonna have the same degrees of freedom at the center of mass of the slab. So if this slab is moving X, is the center of mass moving X, that means all the joints on the slab are gonna move X. That's what the diaphragms do. So right now we condensate all the degrees of freedom in one single point, okay? That's just gonna decrease the analysis time, okay? And that's actually what happened because the slab that we have is rigid. It's however, sometimes there's some slabs that are flexible. There's the standards have some limitations to consider a slab as a rigid diaphragm or a flexible diaphragm, but that's not our topic right now. We're gonna assume, but if you want to read more, you can go in the standards and identify what is flexible, what is rigid, and it's basically depends on depends on the stiffness of the slab and how many openings in the slab. If there's lots of openings in the slab, it's not that rigid, okay? So it's gonna tell you the percentage of the openings, lots of stuff like this, but that's not our conversation. So we made a rigid diaphragm like this, and this is the first thing that we want to do. And the second thing that I want to do, I'm gonna do seismic analysis. So for seismic analysis, if you guys remember, we are not gonna use the entire loads of the whole building because seismic load is a rare event. Maybe it can happen in the lifetime of the structure and may not happen. So it doesn't make sense to design for a rare event for the maximum loading, like we are assuming that an earthquake is gonna happen at the maximum load. By the way, when we said an earthquake, or if we are designing for earthquake, we are designing for the maximum earthquake that can happen in the life of the structure. So from probability standpoint, it doesn't make sense that you assume that the maximum earthquake is gonna happen with the maximum live load and the maximum, all the load on the building. So we are assuming some assumptions, if you guys remember, that it depends on the nature of the live load on the structure. Like if people live in this structure, so we are assuming that there will be not the full live load on the structure. Because when we design a slab for live load, we assume, like when we say 200 kilogram per meter square, that means like two people of my weight are sitting in 1 meter by 1 meter, and that's rarely happening. Okay, so we can do this. So it tells you by the standards that you can reduce the live load on the structure to be 25% if it's a residential building. If it's commercial, it's gonna be 0.5 or 0.25 based on the nature. If it's a library, no, that's 100%. If it's a water tank, we're assuming the water tank is full of water. So it's you can go and find this out in the standards, but to define this, we go to define, and then there's something called mass source. Mass source, basically, we are telling ETAPS, when you pick the mass of the structure, or when you take the masses for solving the equation. Yes, remember, we have this equation, M U double dot plus CU dot plus KU is gonna be equal FT. So basically, if you guys remember, we agreed that the stiffness, we are gonna reduce it, right? Because we are assuming that the building is gonna go into inelastic phase. So this is gonna be multiplied by a factor. And we said that there's something for columns, something for slabs, and something for beams. And also there's another thing for walls. And for this part, we have the mass source, the one that we are going to define. So we are going to assume it's dead load plus a factor, let's say XC multiplied by the live load. This one, sometimes it's 0.25, sometimes it's 0.5, sometimes it's 1, all right? So what ETAPS is going to do for us is going to solve this equation, solve this dynamic equation. And so if you guys remember, this is a second degree differential equation. Once the ETAPS or the software that we're going to use is going to tell you what is when it's getting solved, what is U as a function of T look like. Okay. And if you know UT, you can differentiate it and get U dot, and you can differentiate it and get U double dot. You can get the acceleration of the building. And this is finally is going to be something like this. This is T and this is U as a function of U. All right. Okay. So when we come here, we can go and modify the mass source. Like this is the mass source the structure is using. Mass source, that means the source of the mass in the dynamic analysis. So the source of the mass in the dynamic analysis. So basically the software, what it did is software is saying, I'm going to take all the dead load as the mass source, but I can't see any live load. Like it's saying element self masses or any additional masses, but I want to put a specific load pattern for the software to take the mass source from. So I'm gonna check this box
when I check it, I will see this. When I see this, so I can say, okay, take all the dead load and also take the flooring, because the flooring also is a dead load. And the live load, based on the standard, I can make it 0.25. And then I'm going to add, and then I can say, okay. So right now, yeah, okay. It includes live load and dead load. All right. So right now, the mass source has dead load and has live load by the standards. That's also one thing. And then the next step, I'm going to go define load pattern. I was yesterday trying to define the loads, earthquake X and earthquake Y, but let's do them again. Okay, I'm gonna make this earthquake X1. And so basically, we define, like, do you guys remember this box? We were defining dead load and live load, but right now we're gonna define different type of load, which is earthquake. So I'm gonna name this earthquake X1. And then since this is dead, so you will go here and change it. Once you change it, you will put seismic. Okay, I want to tell you something else. So right now we have two seismic. One is called seismic and one is called seismic drift. Usually when we do seismic analysis and seismic design for buildings, there's a model for the seismic and there's a model especially for the drift. You want to get the drift on the structure. The one that is seismic only, we get internal forces, like we get bending moments, shear, all the forces, okay? The one for the drift, we get only the drift, like the displacement of the building, okay? Why we do this? Why we have two separate models? Because when we design for forces, we design ultimate and we reduce the forces with a reduction factor because of this thing that I told you about in elastic and elastic. But when it comes to drift, and also in the seismic, we increase, okay, in seismic, we reduce the forces and also reduce the inertia. Okay, so both of them, inertia and forces. We assume that the building is going to crack if it got exposed to this amount of forces, like the reduced forces. But in drift, we don't reduce the forces and we keep the inertia the same. Like we assume that the building is in full inertia and the forces are gonna stay the same without any reduction factor. That's how we do it. Well, tell me why we do this? Because there's something called ultimate design and surface design or working design load. So usually when we check deflections or when we check deformations, we check them using the loads without any factors. But here we have to factor the load. It's kind of standard thing. If you guys read more about the standards, how it started as a like working, like there was like a working load and there's an ultimate load. Okay, whatever. So, but not to confuse you and overwhelm you with a lot of standard stuff, let's stick with this one side. We're not gonna escape this drift thing, okay? All right, so I'm gonna pick seismic, and once I pick seismic, you will find that this lateral load thing got activated. Because if you are on dead load, it's not gonna be activated because it's not lateral load. And then it's gonna ask you what the standards that you want to use for this lateral load. I'm gonna say I'm gonna use the ACC 722, and then I'm gonna add this load. And I'm gonna add a copy of this load. I'm gonna say this is Y1. Earthquake in Y direction, and then I'm gonna say it's ESC 7, and I'm gonna say add this load. So let's see what is inside this load. So I'm gonna hit modify lateral load. So when you hit modify lateral loads, because this is a special load, not like live or dead, it's gonna ask you about lots of parameters. Okay, so usually when we do this step, we assume that the lateral load. Okay, so do you guys remember when we said we are converting the earthquake to one base shear is hitting the building? You ask me, where is this base shear is hitting the building? It's hitting the building, it's at the center of mass. So that's when the point of application, okay? But you'll tell me, like, okay, it's gonna hit the building in the center of mass, but this is gonna drag us in a different conversation. We don't want to spend a lot of time on it. So this is let's assume this, we need to differentiate between two things. There is something called the center of mass of the building or the center of mass of the slab and the center of inertia. Okay. So the center of mass, if this is rectangular, so I'm saying that the center of mass here. But if you have like a shear wall here, okay, and a shear wall, let's say here, the center of mass of the center of inertia of this slab is gonna be also in the middle, like something in between these two. But if you only have one of them, so this one is gonna be a little bit shifted, right? That's actually what caused the building to have torsion. Do you guys remember when we said like if you have a building and this building is hold from here and a force hit is gonna make like this. Why it's making like this? Because the force is hitting at the center of mass and it's rotating about the center of inertia. But if you have a shear wall here, so these two are gonna be the same, right? Okay. But the thing is, there's some stuff when we do this that adds stiffness to the building that we don't consider. Like we didn't put stairs in this building. We didn't put many elements. We didn't model in this model. So the standards is telling you, we are gonna assume like there's an eccentricity, even if there's a shear wall here and a shear wall here, and both of them are on top of each other. We are gonna assume that this is shifted a little bit from the center of inertia. Okay. So, and this eccentricity, they say it's a 0.05% from the length of application, right? If the load is hitting this way, so it's 5% from this length. If the load is hitting from this way, so it's 5% from the other length. So that's what the standards do. So we have to have this, but I don't want to overwhelm you with a lot of details. We are gonna uncheck all of these and we're gonna assume, because we only do analysis, we don't do design now. I just want you to do analysis. Okay, so I'm gonna uncheck all of these. I don't want any eccentricity. And I separated X and Y. So you can actually put Y here, but I will tell you at the end why I make it separate. And then it's ask you, what is the, how do you want me to calculate the period of the structure? If you guys remember, there was an equation. If you want to get the period of the structure was like CT multiplied by H to the power X. And CT and X, we can get them from a table in the code based on the structural system. H is the height of the building. So I need to make sure that these numbers are good. So once you go to the table that I have, you will find out that our structure is a special structure and we should pick 0.02 for CT and 0.75 for X, okay? You go check the table, you will find that this number is right. And then it told you what is the analysis range. So I want you to do the analysis from the basis story to the 60 story. Then this box has two methods to do the seismic analysis. So method number 2 is that you give him all the information he needs. Give him the spectral design acceleration at the short and the 1 second, and ask about a spectral design acceleration if the site class is PC, and ask about the long period classification. So we can give all these numbers here. Like I go to the ASSE 7 tool here. I will find out this is the S design, so it's 0.52. So I'm gonna put 0.52 here. And I'm gonna put here 0.23. And if you want to find out the spectral acceleration for site class PC, all you have to do, cancel this and go back here and change the soil from C to PC, and then view results, and then summary, and then you will find what is S1, it's 0.16. So for all of us, I'm gonna give you, so that we all have the same information. So that you don't pick different city. So I'm gonna give you like, take a screenshot of this. and use these numbers. Okay, so that we all use the same number. I don't want any, like, each group use different numbers, because at the end, we want to compare between, we have the same base to compare with. We have the same building and we have the same loads. All right. SDS, this is 0.16. Yeah. SD1, yeah. Okay, so the thing is, our site class is C. So the thing is, I put it as a C and put the numbers, and then I change it to BC because the software is asking for BC. Okay, so, but I don't think it needs the BC for something. I don't know what is it's using exactly, but I put it 0.16, and then it asks you about the long period. The long period is, it's supposed to be if the soil is C. It was like 12 or 8. Okay, it was 12. So I'm gonna put 12 second here. And I'm gonna put the site class C. And then here it asks you about the response modification factor. If you go to the standards, you will find that R is 5. The occupancy factor is the I, the risk factor. So if you go to the standard, you will find it's 1, okay, based on the risk factor. And this one is gonna be 2.5, and this is 5, based on the table that we have from last time, from the presentation. And then I'm gonna say, okay. All right, so I have earthquake X1, so I might delete this load. I want to add the copy of this one. Okay, maybe I will delete this one, and then I'm gonna change this to Y1, and I'm gonna add new lateral load. So let's modify. It's supposed to have all the information that we already. Okay. It doesn't have all the information. Okay, let's try to use our best guess. We have 0.02, and this is gonna be Y, so I'm gonna remove all this. I'm gonna keep Y, and I'm gonna make from 0. The short period was 0.52, 0.23. You guys remember this one? I believe 0.16. Okay, this was 12. Site class C, 5, 2.5, and 5. All right, that's one way to do it. There's another way that we can do this with method 1, but with method 1, you have to do one step before. You have to go to functions, and you have to go to response spectrum and actually define a new response spectrum. So I'm gonna, for example, define a response spectrum. And then you will have to put all the information that we put here. Like you put it's a horizontal response spectrum, and it's a design spectrum, and the design acceleration is 0.52, 0.23. So I'm gonna put 0.52 here and 0.23 here. And then the long period was like 12, and site class C. Once you see I'm changing stuff here, it changed the drawing of the response spectrum, okay, based on stuff that I'm changing here. And then I'm gonna hit OK. And then I'm gonna say OK, right? So then you go back here, define load pattern, and then let's say we are gonna make earthquake X2, add new load, modify. And then if you get to method 1, it's gonna ask you, where do you want me to pick the response spectrum from? I want this one, the one that I just added, and it's gonna add all the numbers that we put here, and then you continue, right? Okay, so I'm not gonna do this now. Let's delete this load. Okay, we already baked method 2, and then I'm gonna.
Take the eccentricity check.
No, we have to uncheck that. Well, when we do design, we need to keep the eccentricity. But right now we are doing analysis. We only do parametric studies, so I don't want to get in more details with the design. But when we design real building, you have to include eccentricity X and Y. You have to include everything. Okay, so that's the thing. Actually, when we do analysis, you might end up having 100 load combination on the building because you want to take into account everything. All right. Okay, so the building right now is ready to run for the analysis. I ran it yesterday, and then because it's gonna take, I don't know, 15, 20 minutes. And once it's done, we're gonna end up having, that's not run one. Let's see this one. Oh, also one thing that I want to mention before you run the analysis, you need to adjust the mesh size so that it doesn't take a long time to run. So make the mesh size like 2 meter, something like this. Same thing for the wall, analyze wall, make the mesh size 2 so it doesn't take much time. And then once you run the building, let's get this ready. All right. Okay, so this is our building. So if we want to look at the deformation of the building, how it looks like. So basically I can get here and then I'm going to show the deformation. It's due to earthquake X, and I'm going to show the contours in the Z direction, not the Z, in the X direction. And then I'm going to say, okay. All right, let's wait, I don't know, 5 minutes. Let's start the animation. Let me put the sound down. But if I put the sound down, the recording is not going to catch my voice. But you guys remind me to put it on again once it's done. Okay, so what I'm showing right now, just for you to imagine how the building is gonna shape with earthquake in X direction. But this is not gonna give us much more information other than visual. But if we want information about the actual displacement, the inter-story drift, we have to have a very powerful tool. It's called a story display or something. So it's gonna show you the display as a line, like the building as a line, and how the stories are moving linearly. So this really takes lots of time to visualize that. That's why ETAPS has a story visualization tool. I think we have to stay until it's done, but yeah. I shouldn't have run it. Yeah, it's too late. Thing is, if I stop it or do something, it's gonna freeze and it's gonna crash. Like immediately it breaches.
But in the 3D, we actually see that the movement of the building, like how far it moves out.
Yeah, you can actually like put the cruiser on the top, but that's not good. There's tools here that can tell you how the shifting without like getting into the video. Okay, it's done now. Can you see? This is how, so we waited like, I don't know, 5 minutes so that we can get this movement. Oh yeah, it shows you color codes based on the displacement, like the one here is the lowest displacement, the blue up there. Oh, yeah, that's one thing. Since we are doing tall building analysis, I need to see the profile of the building all over the product. Like, because that's a tall building product, like sometimes people just put the plan up from the top, but when you show me analysis, I need to see linear information. I need to see how's the building look like. So you need to show me that, like you need to take like the building, like when you put the plan, like when in the description, you show me the plan and the distribution of the column, and also there's a profile of how the building look like. And when you show me the formation, you show the profile, the formation, how it's look like. So that's very important when it comes to tall buildings. Okay, let's stop this animation because it takes a lot from my poor computer. And okay, so what I wanna, this is because what I'm gonna do right now is very, let's turn up the volume. I'm gonna go to analyze and I'm gonna show you how to extract information about the maximum story drift, the inter-story drift, because this is one of the most important pieces in the analyze of buildings, in building analysis. Okay, so you come here and then display, and there's this something called the story response plots. So story response plots, it's showing you how the building is deforming, how's the maximum displacement, but don't get fooled with this. This is the dead load. And if you find the displacement due to dead load, it's like multiplied by 10 to the power -3. But what we want to show is the displacement due to the earthquake load. How much is it? I forgot to tell you something before we run the model. So you guys remember here we reduce the masses, right? But we forgot to reduce the stiffness. Okay, but in your project, you have to reduce the stiffness. How to reduce it? Very easy. Like you will come here to define section, frame sections. We have 5 sections: columns, beams, slabs, and wall, just 4 sections. So you are gonna do this 4 times. You will come to the beams, modify and show property. Write these steps so that you don't forget. And then you will find something that's called modify and show property. So modify and show property, you can reduce all of them to the reduction factors that I showed you. I remember that the slab was 0.35. So you can reduce all of them to 0.35, but the most important thing is the shear and the moments of inertia. Okay, so you reduce these two and also the cross-section area. But I would reduce all of them to the 0.35. All right, so not the mass and the weight, just the stiffness factors. All right, so, and I do the same thing with the columns. I do the same thing with the slab, with the walls, with everything. You will find in all of them something's called modifiers, and then it changed the modifier from 1 to 0.7 if it's columns, to 0.7 if it's walls, to 0.25 if it's a slab. So I'm gonna provide you with the presentation so you can bake these numbers. All right, let's get back. Let's assume that we have done this before the analysis and we have the analysis results. So you will come here and then display the maximum story displacement due to earthquake X. So it's gonna take a minute to calculate this. So here's gonna show you that the red is not moving and the blue is moving, which makes sense because it's an earthquake in the X direction. So it shows you that this building make all this movement. 600 multiplied to the 10 to the power like negative, how much? 0.6 meter. Okay, well, that like maybe not much, but maybe from the serviceability point of view, we need to increase. By the way, this one, the columns was 1 meter, not 1.5 meter. Okay, and the spacing was I guess 3 meters. So your lower spacing, and the beams maybe it's smaller than yours, and the shear walls was 1 meter. So you're supposed to have something less than this number. But I didn't crack my sections. This sections is not cracked. So you have to crack your sections. If I crack the section, this number is gonna get bigger or less? Bigger, right? Because the structure is gonna be more weaker. We're reducing the whole stiffness. So this will maybe reach to 1 meter. Okay. So that means like I need to add more things. Let's say if you got your displacement like 2 meters, don't panic. Okay, that's a trial and error, you know, like, I mean, we are just doing a preliminary analysis. We're not gonna allow this, but if it's 2 meters, we can go with this just to do analysis perspective. But if we're gonna build a structure, it's not like this one. Let it move 2 meters. Okay, so this is the maximum displacement. What does it mean by maximum displacement? Like the whole displacement, there's something that's called inter-story drift. Inter-story drift is basically, the structure complete the displacement here and displacement here and get and subtract them and see what is. So they do this for the entire structure. So if you want to show this inter-story drift or inter-story displacement, maximum story drifts. So you will come here and change this. Okay, so this is how it looks like. All right, you see the maximum story drift, always the story drift shape is like this. Okay, that's the drift shape. The drift is not displacement, like this is not the displacement and this is story. This is the difference between the displacement of this story and this story. And then we plot them. Okay, so basically, if you want to know the difference between the displacement of the story number 24 and 23, you will come here, you will find it's 3.6 or 3.7 millimeter, something like you. Okay, can you see? That's not 600s, that's millimeters between the stories, like 0.5 centimeters. Okay, that's the drift. So I need you for every case that you have to get these plots out, and then you are gonna plot this for every model that you have. Like you are gonna show me, when I did this model, it made this a story drift. When I did another model, make this a story drift. So I can see the trend of how the maximum story drift is increasing or decreasing based on your model. Same thing with the maximum story displacement. Because that's how I know if your model is right or wrong. Like, it's not gonna make sense if you increase the spacing or you increase the depths and the story displacement is getting bigger. So you need to plot all of them in one plot. I believe there is a way here that you can export this to Excel. Like if you come here and save plot. Well, there's something called display, show tables. And when you show tables, element, structure output, story forces, stiffnesses. Here. Summary report. Okay, yeah, maybe you get here and then you click on this table and you can actually export it to Excel and you can copy the column that you want. Okay, so in Excel, you are going to have stories from 0 to 60 and then a column of the displacement, a column for the displacement, model 1, 2, 12, and then you plot all of them in the same plot. Or if you want to keep them separate, okay, like if you want to say, okay, for model 1, this is the result, this is the result, and at the end, this is a comparison between the results with all plots, okay? All right, so we have this done. There's something I also want to tell you, which is the model analysis. The model analysis, I want to find out, do you guys remember the mood shapes that we talked about the building? Like we said, like if this is the building, it can have like a mode like this, a mode like this, mood shape like this, right? So all these node shapes that the building can do, and each one have period, right? The fundamental period is the period of mode shape number 1. If we want to find the results of this, we go to display, show tables, and in show tables, you are going to find out something is called the structure output, and then model information. And in model information, you will go to something called model participating mass ratios. And then I'm going to hit OK. So basically, this one, it shows us that the software ETAPS run 12 modes of the structure. 12 modes. And if you want to show these modes, you guys remember when I showed the deformity shape? I can't show deformity shapes anymore. It's going to take a lot of time. But if you go to show deformation, I make the load case earthquake X, right? There's something called model. You go to model and you pick mode 1. And it's going to show you how the structure of mode 1 look like. And then there's a mode 2, 3, up to 12. You can visualize all the mode shapes of structure. Some of them is going to be torsion. Like you'll find the building is making like this. But let me show you something here. Look at the period of the structure. So here, node number one. Mode number one is like 6.6 seconds. Mode number two, 6.4. And then you will go up to mode number 12. And I want to show you something. It's called the participating mass ratios. Here, you will go to, okay, yeah. So you have here UX and UY and UZ. So it's telling you that node number one that has 6.6 seconds was able to vibrate 74% of the masses of the structure. I mean, like, if this structure is moving with all these 12 nodes, the contribution of node one to vibrate all the masses in the structure is 74%. That's making the dominant node shape of the structure, 74%. And then node number two, can you imagine? UX is almost zero and it's all Y. Okay, so the structure very smooth or the easiest mode is the mode in the X. The mode in the Y is almost a close, 73%. And then look at the contribution. So you have 73 apart to UX, 73% here, and Z is almost zero. And there's rotation, but the rotation contribution is small. Like here, okay, you have 74% is moving in the in X direction, and you have some rotation, like around Y is like 25%. Okay, okay, I want you to look at this. So here, the third mode is not X, is not Y, is not Z. Okay, so let's look at the rotation. So you have zero, and here's almost zero, and let's make this big. Okay, so 0, 0, 0. Look at the numbers. 81%. That means that the third mode is rotation about Z. That means that the third mode is torsion about Z with 81%. Okay, so as a structural engineer, we don't want the verse mode shape to be torsion. The verse mode shape need to be either about X and Y. Torsion is bad. However, sometimes you can't avoid it, but we try to avoid it as much as we can. Okay, so it shows you the mode shape. The standards is telling you that you need to account for mode shape that can vibrate. Because let me tell you right now, when this equation was solved in the structure, it accounted for 12 mode shapes. Let's see 12 mode shapes, how much mass they vibrated. It vibrated 93% of the mass. So that means like there's some other modes that is still not accounted for that needed to make this number 100%. So I need to add more mode shape, but the standards is saying enough was above 90%. If you were able to vibrate 90%, that's enough for me. So I have 93%. This is the summation of all the modes. So you have 93% got vibrated in X, Y, and Z. Where is some Z is 95%. So I'm okay. But let's say in your structure, 12 nodes is not enough, and you need to add more mode shapes. So you have to. Okay, I have to close this, and then you'll have to go to define. There's something here is called load pattern, load cases. And in load cases, you will find model and modify and show. And then you can adjust the number of modes, but you have to unlock the model and rerun the model so it can account for the new modes. So you can adjust from 12 to 20 to 25 so that you can make the mass participating mass ratio for all the modes more than 90%. Because once we do the design or do the analysis, that means that the total mass that we accounted for is 93% of the mass, because we didn't account for other nodes, right? Okay, so I don't want to get you in deep in this. Let's close this and talk about something else. Right now, we make sure that it's 90% and everything's good. I want to teach you something else because that's very important for the project. Okay, so I'm gonna show the undeformed shape. what is the other important thing that we need to talk about? Do you guys remember? We need to find drift, interstory drift, model analysis. What things that we talked about that we need to present in the project? Shear lag, right? Okay, I'm gonna show you how we're gonna print this or how we can show this. All right, I'm gonna show set 3D view for the entire structure. I'm gonna pick all the columns here, and this is in the versus story. I mean, I picked all the story, but I'm gonna go to display, show tables, and I wanna show what is the normal force in these columns, because that's what is gonna lead us to the shear lag, right? Okay, I'm gonna uncheck this. And then I'm gonna go to elements output. Okay, if I came to this table and want to show elements output and I didn't select these columns, it's gonna show me the element output for all the structure. So that's why I make a selection. So I don't care about the other columns. I just need the versus story. And then I'm gonna hit frame output. Okay, and then I only interested in element forces on the columns, not on the beams, okay? I don't want the beams right now. And I'm gonna select the load patterns that I'm interested in. Right now I'm interested in X direction. So I'm gonna hit only X direction. And the load cases, I make sure it's only X direction because you are gonna get overwhelmed. The table is gonna have a million number. So I wanna only focus on the columns in the versus story and the normal force during to earthquake X. Earthquake X is gonna make like this. I wanna find what is the normal force in these columns look like. And I'm going to say, okay. And here I'm hitting selection only to make sure it's only the selected columns, and I'm gonna hit okay. All right, so it's gonna show me a table like this, telling me that at column 1, there's all this information, but there's 3 column 1s. That's what it taps to. It tells you what is the normal force at 0, at 1, at 2. What is 0, 1, and 2? It takes a section at the column. But I'm interested only at the base of the column, okay? So I'm gonna filter this column to be only at the bottom of the column, okay? So what I'm gonna do, I'm gonna take this table to Excel. So I'm gonna say File, Export Current Table to Excel. Okay, and this is going to be exported, and I have it here. So when you have it here, it's gonna be 2 sheets. I'm gonna go to sheet number 2 that has the column forces, and this is the Excel sheet that I have. So right now I wanna plot how these normal force look like. But the thing is, I wanna make sure that these columns are arranged properly, because if you plot these, it's gonna be random. I wanna make sure that I'm only plotting the column on the edge, and they are all like 1, 2, 3, 4 up to 10. I don't wanna have column number 10 in the table is like another column in a different side, okay? That's one thing. And the other thing, I want to filter this. So I'm going to filter this to only section 0. So I'm going to do this. I'm going to go to filter. And then I'm going to say, I want to filter this to be only 0. Okay, so right now we have column 1, column 2, only one number. Second thing, if I want to make sure that the number is good, so I will go back here. I'm gonna show, for example, story or plan for story number 1. And then I need to show the columns numbers. You go to display, set display options, and then you will go to object assignment. I want to show labels on the frames, not the joints. Frame assignment. I'm gonna hit OK. Labels. Okay. Yeah. All right. So I'm gonna come here and see the numbers of the column. This column is number 64, and then we have 41. And here we have C1 22. So let's make this. We have from 22 to 41. They are all together, like 22, 23 until 41. But the verse and last are different. So what I'm gonna do, I'm gonna go to the table that I have here. I'm gonna make another sheet. I'm gonna look for column 22 to 41. This one, I'm gonna copy this and I'm gonna get to this sheet. I'm gonna put them here. I will get back here and see what is the value of force B, which is the normal force from 22 to 41. Control C. I'm gonna put these forces. Then I believe we have C1 at the end. So I'm gonna go big C1, Control C. Let's name them C22, C23. Okay, we have here C1. And we have at the end, do you guys remember the number? 64, right? Okay, we'll go back to the Excel sheet and then search for column 64. This one, this force. All right, and I'm gonna put it here. I'm gonna here put it C64. And let's plot this and see how this is gonna look like. By the way, let me ask you, which age that we picked? This is earthquake X going this way. And we picked this side. How's the shear line supposed to look like? Is that the one that makes like this or the one that makes like this? That's the one like that has the stresses, tension, and then 0, 0, 0 until it goes compression, right? So that's how it's supposed to be. But this one is supposed to be all tension, right? Okay, so let's see when we plot this, how it's gonna look like. I'm gonna draw, or actually we can insert this, and we can make something like this. All right, can you see? That's how it's look like. So we have it something like this. So I believe it makes the negative C1 actually was over there, and C64 is the one that is positive, that has tension, right? Okay, so that's how it looks like. We can do the same thing for the other side. Like here, the other side is C64 and going up all the way to C84, and then we have C63 in the top. Okay, so from C64, yeah, this one. Okay, 64. And then until 80 what? Okay. All right. And actually we have 63 as well, so we can change the location of 63. I'm gonna put it here. So I believe that was 63. We're gonna take it Control X and put it here. And this one was C64, C65. And we are going drag until we come here. Actually, let's put it here, and we change the name of this to be 63. Then we can plot this one, and actually that makes sense. All of them are positive. So let's plot this, insert, and this is going to be something like this. How's the shear lag look like? And actually it looks decent, right? So what I want from you, you are going to do this for the two sides. Actually, it doesn't make sense to make the other two sides because it's almost symmetric. So it's going to give you something like this and something like this. I want you to show me to take this, to do the same thing like I did for the 12 models. And rather than having one column here, we're going to have model 1, model 2, up to model 12, and plot all of them on the same curve. Or you can plot them separately, whatever you want. Like Because I want you to do the same thing at different stories, like we did at the basic story, try to do it at the 10th story. And maybe at the 40th story, maybe 3 or 4 of them. And see how it's gonna look like, because this is gonna be different. The shear line getting less, even at some story it becomes almost 0. Except the corner columns, because the corner columns are always stressed. Okay, so I want you to do this for every model, maybe plot 3 or 4 of them at different story height. Do them for all models, and then I want one curve at the end after we finish the 12. Plot maybe all the curves at the basis story for all the models, and plot all the curves for the story number 10 for all the models, and see how the shear lag is changing. Okay, for both the side and the front. Okay. All right, and I told you about the bonus, how we do it. Do you guys remember? We need to calculate the inertia. There was a lecture in the recording how to do this, right? Okay, last thing about the, it's gonna take 5 minutes, about let's come to plan, let's say story number 15, about the outrigger. Let's say I'm gonna put in story number 22. Outrigger is very easy. The same way that you draw a shear wall, maybe the shear wall is supposed to be the wall to be the same thickness of the column. Because you can't, because outrigger is gonna be like a deep beam. It's gonna have a column from the top, column from the bottom. The column can't be outside the deep beam, right? So it needs to be the same thickness of the column. So, for example, I'm gonna draw like a belt. Here, I'm gonna say it's wall 0.7 meter, the same wall. I believe it's much smaller than the column, but okay, but you try to make it like the same. All right, right now I made the build of the outrigger. Okay, so the second thing I want to make the same thing like outrigger connecting the shear wall to the outside build like this. And I'm gonna do the same. Here from all direction. And I'm gonna do in the other direction here. And the other direction over there. And you are gonna make this at the same stories that you have in your project, and then run the model, and the outrigger is done. Oh, I made this not right, but you should make it right. So that's the outrigger. That's all what we need. If these 2 columns are on this wall, that's much better. But if it's not, that's okay. All right. So, and then run the model, get the shear lag, get the interstory drift, and I expect at the story that has the outrigger, the interstory drift is gonna be almost 0. Like you'll find that the story drift is looking like this, and then goes back, and then goes all the way down. Okay, because that's a stiff wall, like it doesn't deform much. So it's gonna affect the displacement, it's gonna affect the interstory drift, affect everything. And if you want to add a third outrigger, add the third outrigger and see how it's gonna affect your model. So I believe I covered everything about the modeling. Maybe over time, if you stuck with the bracing is easy. You view the side view and you just keep drawing the columns story by story like this to make the bracing. But if you stuck with this, I can definitely help you with that. And it's a bonus, so you guys are all covered. Does anyone of you have any questions? All right, so we are done with the project. We have been like over a month explaining everything. So you are supposed to go, and we are going to conclude short analysis for the rest of the semester. Okay. Good luck, guys, with the project.